teach about phase rule. So the phase diagram are equilibrium diagrams. So I want to make it simple and shorter. So let me move it to the phase rule. So the phase rule is we have to count the freedom, the degree of freedom. So F equal to C plus 2 minus P. So you have to know that C is for the component and P is meaning to the phase present. So we learn to one component system first. So this is the phase rule diagram. Example of one component system is water. So this is a water diagram, phase rule. Pressure versus temperature. Okay, as we can see, this is ice, water and vapor. So the diagram, it has to be divided by 3 parts: the area and the curve, and also the last is the melting point. So if you want to calculate from the area, so let we see from A, O, B. This is area. Okay? So A, O, B is equal to ice. So if you want to calculate, use the formula that I have shown earlier. So F equal to C plus 2 minus P. So the component equal to 1 because we use one component system. So F equal to 1 plus 2. And we see at the area of AOB is the ice. Is only 1. So minus 1. So if we total all of this, 1 plus 2, 3 minus 1 is 2. So the degree of freedom for AOB area is 2. Okay. After that, the curve. Okay, let me see the curve. For example, AO. The curve is here. It's sublimation because ice goes to the vapor, solid to the gas. So it's sublimation. So we use the formula that I have written earlier. Use the same formula. F equal to C plus 2 minus P. So the component is equal to 1. So one component system plus 2 minus P. P is the phase. As we can see, the curve AO have 2 phases, ice and vapor. So we put phase here minus 2. So 1 plus 2 equal 3 minus 1 minus 2 equal to 1. So the freedom of the diagram for the curve AO sublimation is 1. So that's how you calculate the freedom of the diagram on the phase rule. Thank you.
Assalamualaikum. Today I will present about binary system. Binary system consists of 2 components. But when the components mix together, it will result in mutual solubility and solid solution, and partial solid solubility, which consists of partial solid solubility with formation of intermediate phase and without formation of intermediate phase. Next, we move on to graph, phase diagram. Solid solution. There are 2 types of solid solution. First, substitutional and interstitial. For substitutional, the ion directly substitute for the host ion which is nearest to it in electronegativity. For interstitial, the ions are so small, so they dissolve in the host crystal. Okay, now we proceed to our phase diagram. In this diagram, we have 4 phases: solidus, solid solution, liquid solution, and liquidus. This is in the middle we have liquid plus solid. At T1, which is this, the solid solution of of magnesium oxide and nickel oxide will start solidifying. So, which means it is in liquid solution, but after this temperature, it will start solidifying to be more solid. Next is T2. T2, the approximate temperature is 2,500 degrees Celsius, where two phases coexist, which is solid solution of composition Z, solid solution, and liquid solution of composition X. At temperature 3, approximately of 2,400 degrees Celsius, final liquid solidifies. So the final composition of solid solution is now same as initial composition. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. And now for eutectic diagram with partial solid solution and no intermediate compound. From this graph, most ceramic battery phase diagram exhibit partial solubility, which means it's not fully solubility. And if we add one component to another, the freezing point will be decreased. So you can see this is Xe. Xe means eutectic composition, and T is eutectic temperature. And the lower liquid is curves for both end members, which is intersect at a point. And the lowest is at which liquid can exist eutectic temperature. And this is L equals to alpha plus beta. Okay, this is reach just below TE is TE. There is two phases of very different composition. This is rich of calcium and magnesium. This is 65%. And next is partial solid solubility with the formation of intermediate compound. In one condition, the solid solution domain is the absence of strong affinity of the end members of one another. But in other case, the two end members they call intermediate compound. Example: AX/BY/O2. And intermediate compound melt divided by 2. First is concurrently melting intermediate compound. Example: Na2O(S2) SiO2 and Na2O SiO2. This no changing in composition. The next is spinel, MgO Al2O3. There is two eutectic phase. And next is incongruently melting intermediate compound. This is the compound dissociate before melting into liquid and another solid. So this phase diagram become more slightly and less complicated. Thank you. That's all.
Okay guys, so today I will explain a little bit about ternary system. So ternary phase diagram relate the phase which is T in a 3 component system. So there is 4 variables which is T, P, and concentration of two components. So the three components are represented by an equilateral triangle in a 2D dimension, which is like this. So the boundary curve represents equilibrium between two solids and liquid. The intersection of the boundary curve represents four phases in equilibrium. This point is the lowest T at which liquid can exist, eternally eutectic. So I will teach you guys how to read the diagram. So we have the component which is AO, BO, and MO, and we have 2 points, which is point X and point Y. So how do we read point Y, for example? So I will draw the diagram. This is the triangle, and this is point Y. Okay, so this is MO, BO, AO. So how we read this is on this side we will put the numbers or the percentage of the composition for MO, starting from 100% here and going down to 0% here. So for BO we will do the same, but for this side, and for AO we will do the composition the same from this side, which is this is the 100% and going down here. So 80% mole MO means that at the MO we draw a straight line that intercepts the point. Then when it intersects, we from the point we make a perpendicular line towards the side that has the composition of the MO. So it will touch here, which will read at 80% mole, and it is the same for every reading. So any ternary phase diagram that does not include a solid solubility region will consist of a number of compatibility triangles. Once the compatibility triangles are known, both the phase present at equilibrium and the relative amount can be determined. That's all from me. Thank you.